All right, let's go ahead and begin. Welcome everyone. I appreciate your time today and joining us on our webinar. My name is Kevin Jamison. I'm president at PureAir Filtration. Welcome to our series of monthly webinars. This month's webinar is entitled Selecting Systems for Wastewater Odor Control Applications. And we note that odor is spelled two ways there. There's a kind of the British way and the American way. We work on odor control applications all around the world and have to make sure we accommodate both spellings. So this presentation today is somewhat an introduction. I've noticed some of the attendees who've signed up for this are very experienced odor control consultants and such, so they may or may not find new information here, but certainly if you're new to the odor control industry or looking for a refresher, hopefully today's seminar will be of interest to you. So let's go ahead and get started. So first, let's take a look at considerations to make when looking into odor control. So keep in mind some things when designing odor control systems or selecting odor control systems. The key is each odor control application is very unique. I don't think we've ever repeated the same odor control application. Sometimes we're able to use the exact same system, but the applications are always slightly different. A little different airflow, a little different odor signature. So we always like to keep total odor control in mind when looking at odor control. We see a lot of work in the industry where there's a focus on just hydrogen sulfide control. And hydrogen sulfide control is very important, but we have certainly run into a number of applications where hydrogen sulfide was the primary concern, but other odors existed and generally were not addressed. That takes some work to get that addressed later on. So we try to take a look at complete odor control, not just hydrogen sulfide. So one of the keys we think in regard to designing a system is allowing for some flexibility. You can always think that you know what the conditions are for odor control, but just as soon as you think you know, they change. And it may be that you're designing an odor control system that for a site that doesn't exist yet, so you've got to try to guess at what the odor situation would be. And the other is that odors situations change. You've got seasonal fluctuation, you've got fluctuation due to increased occupation on maybe or increased utilization of a lift station or just further utilization of the collection system. And so the situations change, and we always think it's a good idea to make sure that the system which you've designed or selected offers some flexibility. Obviously, we always have to allow for access and operation and maintenance, very, very important, and certainly understanding the abilities to maintain it once it's in operation. So we have some customers who are really, really good at maintaining systems, any kind of mechanical system. We have other customers that maybe you're a little more interested in just fixing things when they're broken. And so it's good to know your level of interest of a client as far as providing some kind of maintenance to the system. So let's talk about the different types of odors. So, you know, there's fresh sewage odor. That's basically referred to as fecal odor. And that is, you know, sewage that's come just from the houses and such. And so that hasn't developed a whole lot of hydrogen sulfide. Of course, there is hydrogen sulfide. That's the primary focus of the odor control industry. Without a doubt, 99% of what we're removing in most of our applications, we are focused on hydrogen sulfide. Where there is wastewater odor, there is most likely hydrogen sulfide. So it's important, but also to keep in mind mercaptans and other reduced sulfur compounds, ammonia and amines, and even volatile organic compounds can be a case as well too. So, you know, these reduced sulfur compounds here in this area, those can really be nasty odors at very, very low levels. We'll talk about that a little bit more, but it's important to make sure that you're addressing those as well. So if you're not familiar with a lot of odors, here is some description. This is some information that's commonly found on the internet about various types of odors. So, you know, I think everybody is generally familiar with hydrogen sulphide. It's kind of a rotten egg smell. The key is look at the odor threshold for hydrogen sulphide. In this particular citing, it mentions 3 parts per billion. As far as at what level you can smell hydrogen sulphide. So at 3 parts per billion, that's a pretty low level, and that's why hydrogen sulphide gets focused on so much, because you can smell it very low. But look, here mercaptans are measured in the part per trillion level. We've got plenty of others in the parts per billion and parts per trillion level. But you take a look at ammonia, we're typically only smelling ammonia in the parts per million level. So we get a lot of inquiries where people are looking to take odor out of a wastewater application, and they're concerned about hydrogen sulfide and they're concerned about ammonia. Generally, we don't see ammonia creating many odor issues, typically because you just don't smell odor at fairly low levels. And so just want to mention to you that you really have to understand what's the beast that you're working with, and trying to tame that beast. And certainly some of these other odors are much harder to work with, to tame, and others are a little bit easier. So how do you go about figuring out what odors you have in your system? So let's say you're working on an existing application, you've got an odor problem, you need to define what that odor problem is. So there are some very good tools on the market that are readily available for you to work with. Many of these tools can be rented or purchased, of course. And so we'll discuss a couple of them. Probably one of the biggest tools in the industry is the Odor or ACRU log. So the Odor log is this device, and it's been out for a number of years, certainly more than 15 years, and it's been really a standard in the industry for collecting hydrogen sulfide data. Very nice tool. Unfortunately, it has gotten a little out of date as far as some of its capabilities, and along comes the ACRU log as a competitor, and offers some really nice interface, Bluetooth connection, and even a cellular connection as well to it, so you can check on your data remotely. Very nice device. You can easily find these on the internet. They're distributed in the US by Detection Instruments. We're really good people. Certainly would recommend. Both of these devices are distributed by Detection Instruments, but I definitely recommend looking at the ACRU log. It's a very nice product. So if you're just looking at taking hydrogen sulfide readings, these are very easy to use devices. Pretty much turn it on, it starts collecting data. You leave it in there for whatever period of time you're interested in. We typically leave it in for at least a week, and then you retrieve it, turn it off, and download the data, and it gives you a nice historical record. You can set the log to collect data how often you want, but usually we set it to take a reading every couple minutes. So in addition, there is the Draeger tube analysis. So this is a Draeger tube and pump. And Draeger sells these tubes that are full of a color-changing chemical, and it has an air pump that comes with it. You put the tube, it's a disposable tube, you put the tube into the pump and you pump it the prescribed number of times to pull the odorous air into the tube, and that chemical that's in there will change colors depending on what chemical you're looking for. So if you know what gas you're looking for, if you're looking for hydrogen sulfide, if you're looking for ammonia, if you're looking for mercaptans, then you select the tube for that gas, and you pump the air through there to measure how much of that gas is there. So there's a color changing, a graduated glass tube that will correlate to what the gas level is. Now just keep in mind that gas level is just for that period of time that you were doing the pumping, whereas an odor log is giving you a record over an extended period of time. I'll mention as well, there is the Jerome Gold Film Analyzer. This is the latest model from Arizona Instruments, is the Jerome Gold Film Analyzer. This is kind of the standard in the industry for high accuracy. It is a very expensive device, and it certainly is more bulky than the Odolog. But if you're looking to take low-level measurements, if you're looking to have the best device that's out in the industry, typically the Jerome is considered that with it. So a very nice device to have, especially for measuring low-level, maybe outlet concentrations of odor control systems. It's an excellent device. I'll also mention a process that you can use for collecting an air sample on. It's referred to as a Tedler bag process. And typically what you're doing is using a pump of some sort and filling a bag, a Mylar bag, full of the air which is of concern. So if you can fill that bag up and you send it back to a laboratory, and that laboratory will perform a test of the gas that's in the bag. So it's a very, very nice, if you don't know what gas you're looking for and you need to define what gas is in there, this is a great way to do it. There's actually a couple of different tests that you can perform. One actually speciates the exact gas using spectrometry. Always have problems with that word. And tells you the exact gas and its concentration. Another, though, is testing with an odor panel, and that means actually having people with well-trained noses smell the gas that's in here at various dilution levels, and they're able to determine the concentration of the gas or by diluting the odor until they can't smell it any longer, and that's called an odor unit. So if you send them a bag of gas and they come back and tell you that it's at 100 odor unit, that means they have it diluted 100 times until they couldn't detect any odor level any longer. So this gives you a good way of determining the severity of the odor, let's say. Also, just the good old human nose is certainly available for your use. I'll certainly have selected a number of odor control systems based on noses or number of complaints or distance from a source as far as when you can smell it or how objectionable it is. It's certainly not very scientific, but it is practical from that standpoint. Just keep in mind, everybody's nose is different. Some people have very, very sensitive noses, and some people don't have very sensitive noses at all. So if you're going to use a nose to try to figure out what kind of odor or how bad your odor is, you might want to depend on a few different people's opinion in that regard. So, in summary, there are lots of different types of malodors, bad smelling odors, and the level and mix is constantly changing. So when you're selecting a system, you have to keep in mind that these malodors are detected at extremely low levels in the ppb or parts per trillion levels. And different odors may need different types of treatment with it. Not every odor is the same, and so you need to consider that when you're taking a look at the odors. And typically, we recommend that you design your system to be effective at all odors which are present. Don't just focus on hydrogen sulfide. We've seen lots and lots of cases where, as I mentioned before, hydrogen sulfide is the focus, and the system does a great job of removing hydrogen sulfide, but it leaves behind a lot of other odors which people are unhappy about. So today we're going to take a look at odor control technologies. In general, we are going to focus on just 3 technologies. These are kind of 3 standard technologies that are used in the odor control, especially the wastewater odor control market. So the first is adsorbent systems. The second is biological systems. And we're going to spend a short amount of time on chemical scrubbers. I'll be very frank with you, I am no expert on chemical scrubbers. And so I don't offer a whole lot of expertise in that area, but there's a little bit of information in here that I can assist with. So taking a look at those 3 technologies, what do those 3 technologies have in common? And they have one thing in common. They all need some type of physical or chemical contact to remove the malodors. The mechanism, it's just the mechanism, the difference in mechanism that separates the technology, right? So they have to have some contact of the odor in order to remove it, to reduce it, to react with it, to eat it, and being able to understand the amount of contact and the type of contact that has to happen is very, very important when taking a look at these odor issues. We'll also just mention to you, when you're taking a look at systems selection, the type of technology that you're going to use, you definitely want to be interested in the efficiency of the removal, the reliability of the system, initial cost, operating cost, footprint space, ancillary buildings, if you need storage of chemicals and such as far as it goes. Of course, a big issue I've already mentioned before is maintenance and operational concerns, understanding the willingness of your client, how much time they're willing to spend with the system. Hazardous chemical handling, very, very important these days. Some of these systems can use very hazardous chemicals, so you want to make sure whether a client is ultra concerned about that. And then, of course, aesthetics and noise are big issues in the industry as well. No sense in fixing an odor problem and creating a noise problem for neighbors. So here's a selection chart that I've come across in taking a look at various odor control systems. Now, this doesn't mention chemical scrubbing, and I think that I'll probably work on adding, talking to some friends in the odor control industry and adding some information in here about chemical scrubbing. But this is a selection chart you can generally take a look at based on hydrogen sulphide levels versus airflow. So in general, the higher your airflow goes up, various technologies become more and more significant, or the higher your H2S level or odor level in general, but especially H2S level, then other technologies tend to take over. And in some case, typically a hybrid technology might be used where two technologies together provide a solution as well. So we'll be able to send this presentation to you afterwards. We'll send the presentation in case you want to reference this particular one. And when we update it to include chemical scrubbing, we'll send it to you as well on there. So first type of technology we're going to take a look at is adsorbent technologies. So very often this is referred to as activated carbon technology, and that's the basis behind the technology, but there are a lot of other adsorbents that are available on the market these days that go beyond activated carbon. So let's just take a look at activated carbon. For activated carbon, sometimes people refer to it as charcoal. It's charcoal with an additional step, this activation step. And generally, activated carbon has been used for a long, long time for capturing odor, purifying air. It's a good general odor capture. It captures lots of different types of odors. In general, it has a low capacity for inorganic odors. All right, so it's great for organic odors. Volatile organics it's really, really great at. But in general, for inorganic odors without a carbon molecule, it doesn't do very, very well. So keep in mind, activated carbon is the carbon molecules, and carbon is attracted to carbon. And so inorganic molecules that don't have carbon typically do not have a great affinity for activated carbon. So also keep in mind that activated carbon it's actually a physical process of holding odor. So these odors go into activated carbon and they're held inside, but they can actually be desorbed. So as they get adsorbed into activated carbon, they can actually be desorbed, and so you can actually have odor come out of activated carbon. So you need to be aware of that, be careful, especially when the activated carbon is near the end of its life. It's been fully consumed, and it tends to let some of that odor out occasionally. One of the issues as well with activated carbon is there's no real practical way of measuring the remaining life of the activated carbon. So typically these systems run until it starts smelling again, and then the customer scrambles real quickly to replace the activated carbon and put the system back into operation. So that's the original adsorbent. Over time, engineered adsorbents have been developed. These engineered adsorbents are typically using a chemisorption principle to target particular gases. We're going to talk about chemisorption coming up. So engineered adsorbents are basically taking activated carbon and other substrates and beefing them up and getting additional performance out of them. We'll also talk briefly about scavengers. Scavengers are just low-cost roughing products for focusing primarily on hydrogen sulphide. So we'll look at an example of that as well. So the technology for adsorption is also referred to as gas phase adsorption. So how does gas phase adsorption work? So these adsorbents, activated carbon being one of them, have have a huge number of pores inside of them. These are microscopic pores, very, very small, and they're typically just a little bit larger than the molecules that are being adsorbed. And so what happens is these molecules, these odorous molecules, are typically find their way into the pores of an adsorbent, and they're trapped inside. And in activated carbon specifically, there's a weak molecular attraction that holds those molecules in the adsorbent, all right? And so it's kind of a magnetic principle. If you think about it that way, it's a van der Waals effect is what the technical term is. But basically, molecules stick to molecules, and in this case, odorous molecules go into the activated carbon, and they stay in there in most cases. Sometimes they desorb. So that's generally how gas phase adsorption works. Let's talk about the difference between adsorption and chemisorption. So adsorption is spelled, and I'm referring to it with a D. So there's a difference between absorption and adsorption. So adsorption with a D is when something goes into a adsorbent, it's captured on the inside. So it's very much a principle like a sponge. If you think of an adsorbent to be like a sponge, activated carbon is like a sponge for gases. If gases go into activated carbon, it's just like water going into a sponge. It's bound onto the inside, and it's kind of carried throughout that entire sponge. But like a sponge, if you squeeze a sponge, the water comes back out. The same thing can happen with activated carbons. Under the right conditions of a stress, typically a change in temperature, a change in pressure, a change in humidity, those gases can come back out. So that's the adsorption and desorption principle with plain activated carbon. So a subset of adsorption is referred to as chemisorption. Now, chemisorption is when the adsorption principle is used, but a chemical is added to the adsorbent. The chemical, the gases go into the adsorbent, and then there's a chemical reaction that occurs while it's in there, and the gas is converted into a solid and held on the inside permanently. So it would almost be like, well, it's a sponge, but a sponge where you would have a chemical reaction and the water couldn't come back out of the sponge. So that's the principle of chemisorption. And generally, that's the principle of what most modern adsorption systems work with, is a chemisorbent of some type. So just to give you an idea about these pores that I've been speaking about, here is a micro view of activated carbon. And you can see under an electron microscope what these pores look like. These typically were originally the cell walls of some plant, prehistoric times, but before it was turned into activated carbon, if it comes from coal or whatever the substrate was ahead of time. and gases go into these pores and they bind into the side of these pores. Now, the incredible story about activated carbon and why it works so well is that 1 gram of activated carbon has about 1,100 square meters of surface area. So if you counted up the area of the surface of every one of these pores of 1 gram of activated carbon, you get about 1,100 square meters. That's about the size of a football field. All right. So if you spread out activated carbon, you could spread it out across a football field. So it's just an incredible amount of porosity, and we use that porosity as an advantage when working with absorbents. So again, adsorption is a physical process. It's activated carbon, typically it's reversible. Chemisorption is adsorption plus a chemical reaction, and typically you're working with impregnated carbons or catalytic carbons or some other type of physical and chemical reaction. All right, sorry, I'm at a little bit of a delay on my, just a little more, just some quick information, activated carbons. Keep in mind, activated carbon is carbon can be lots of different forms. You can have coal-based carbon, you can have coconut shell carbon, nut shell carbon, lots and lots of different sources for the charcoal, which is the basis of activated carbon. The key with that is different types of activated carbon have different pore sizes, and different pore sizes are better or worse for capturing different molecules of different sizes. So very often in our industry, people focus on coconut shell activated carbon. There is a misnomer about coconut shell activated carbon. It is one of the best activated carbons as far as capacity goes, but mainly for capture of volatile organic compounds. It really doesn't have any better capacity for inorganics such as hydrogen sulphide, but there's a misconception in our industry that coconut shell based activated carbon is the best activated carbon. It is the best activated carbon, but only if you've got a VOC, a volatile organic compound application. In general, just about all other plain activated carbons have about the same capacity as coconut shell activated carbon. This is a graph showing how activated carbon works. I mentioned to you there's different pore sizes, so different activated carbon have a different spread of different pores. They're called macropores, these large pores, and micropores. There's a mid-range one called mesopores. So large molecules get caught in large spaces. Small molecules can feed down into these channels and get caught in small spaces. So that's why certain activated carbons work better for certain gases than others do. So a activated carbon with a high amount of microporosity is very, very good at capturing very small molecules. One with larger porosity is better at capturing large molecules. So that's the difference between activated carbons. So we often get questions about carbon regeneration. So if you're using activated carbon, and we do use some activated carbon in some of our applications, can that activated carbon be regenerated? Well, the question is, it can. I mean, the answer is yes, it can be. There's actually 2 types of regeneration of activated carbon which are possible. We'll just address those real briefly. The first is a kiln desorption regeneration. So I mentioned to you that activated carbon has the ability to desorb the gases that it's caught. And so if you take an activated carbon and you return it to typically an activated carbon manufacturer, or a specialty regeneration site, they will actually run that activated carbon through an oven, and that will actually heat the activated carbon up so much that all the gases that it collected, or most of the gases that it collected, will actually leave the activated carbon. Typically those gases would be then burned in the furnace, and the activated carbon can then be put back into use. That is, the difficulty there is you have to actually remove the activated carbon, you have to send it off to a site, it has to be regenerated and then returned back to the site and refilled into the system. And generally, a lot of customers don't find that to be practical to do it, and instead just dispose of the activated carbon and buy new activated carbon. I'll mention to you that generally this activated carbon does not return to 100% state. That's what's referred to as a virgin activated carbon. Is the first time it's never been used before. And after you use it, then it might only have 80 or 90% of the capacity. So it's generally considered a diminished product, but it does have some value. So some applications certainly can use that as well. I'll mention that there has also been in the past in situ water regenerated carbon. So this is a very special type of activated carbon. And the key here is that you can wash the hydrogen sulphide that it captures out with water. Water will actually, sorry about that. Water, when an activated carbon vessel is filled, where the activated carbon is full of hydrogen sulphide, when it's filled with water, that water will convert the hydrogen sulphide to sulfuric acid. And if you just repeatedly wash, fill and empty the activated carbon vessel, you will eventually wash the hydrogen sulphide out of the carbon, and then you can return it back to use. But there's lots of issues with that process. It works really great in the laboratory, but the reality is, in odor control, there are other odors than just hydrogen sulphide. You've heard me talking about that. Those odors are not washed out in this special carbon. And so in that case, what ends up happening, and even though in the laboratory, when you fill activated carbon with hydrogen sulphide, it's very easy to regenerate it. In real life, those other gases fill up those pores and they stay filled up, and it prevents the activated carbon from returning to 100% consumption. And so what really practically happens in this water regeneration carbon is the first time you get your original life out of the system, and then it drops by about 20% capacity after you water regenerate it. And then after you water regenerate it a second time, it's down to 60% capacity. And soon the product just simply can't be washed again because it's full of other types of gases. Also, you use a lot of water during that time. So in certain areas of the world, water is a real is a precious resource. So you end up using a lot of water. And it should also be mentioned that these systems are typically unavailable for days at a time while doing this regeneration, because you've got to fill the system up with water, you've got to let it soak, then you've got to empty it, and then you've got to fill it again. Typically it's maybe about 5 times that you have to do that. So in the meantime, the system is down. Very often we see customers with this type of technology needing a second system just so that one system can be regenerating while the other system is working in kind of a duty and standby mode from that in general. So we haven't seen, this technology is basically faded from the market due to a lot of installation issues and customers not being satisfied with it. It does exist in some cases, but generally it is a technology that did not meet its potential. So we'll talk about chemisorption. Now, chemisorption, I mentioned to you before, is absorption plus a chemical reaction. So this is an addition to it. This is basically a process of instantaneous, it's a process which is instantaneous and irreversible. So these gases go in to an adsorbent, they go through a chemical reaction, and then they are converted to another molecule, typically a solid, where they're held in permanently. So generally, after that reaction, the product is non-hazardous because you've taken a product like hydrogen sulphide and you've neutralized it, and it's typically pH neutral at that point in time. So that's how chemisorption work. There's various types of chemisorbents. Here's a photo showing some different shapes and sizes and colors of chemisorbents. There's two parts to a chemisorbent. There's the substrate, which is the solid portion, which has the pores. We talked about activated carbon. Another one is aluminum oxide. This typically goes by porosity or surface area. So activated carbon has the highest surface area, about 1,100 square meters per gram. Activated alumina is what this product looks like here. It's aluminum oxide, so it's kind of a ceramic bead, a porous ceramic bead. It has about 350 grams per square meter, per gram, 350 square meters per gram. Zeolites, natural zeolites, are just a very low cost porous product. Generally, there's a bunch of different types of zeolites, but most of the zeolite that used is kind of a low porosity product for low, not very critical applications. Typically, maybe a commercial application for indoor air quality. And then there are some porous clays which are used as well with that, especially when it comes to scavengers. So this is your substrate, your porous substrate, and then the chemicals that are added to do that chemical reaction, or the chemisorption reaction. So there's various caustics. A very popular one is potassium hydroxide or sodium hydroxide. They're basically the same. That used to be a very, very popular product, but that its popularity is diminished greatly because of an increased possibility of fire with the activated carbon. So keep in mind, activated carbon is charcoal, just like the charcoal that you grill with. And when, in this case, KOH impregnated or sodium hydroxide impregnated activated carbon actually catches on fire easier than normal activated carbon. So there have been some instances of carbon fires with this product. So it's still in the market some, but generally not used a lot. You can impregnate with acids. Typically, if you're going to be removing ammonia, you might use an acid to neutralize ammonia. Oxidizers are heavily used. This purple chemical here is actually potassium permanganate, which is impregnated onto alumina. Very, very popular and a strong oxidizer. So that any gas that can be oxidized is oxidized by potassium permanganate. So that's a very broad range acting product, has a nice color changing ability as well, which is helpful. And also I'll mention catalysts. So there's a number of catalyst chemisorbents available as well, typically working with activated carbon, where a catalyst is added to the activated carbon and the catalyst is used to react with whatever gas is being catalyzed, typically hydrogen sulphide, and that results in a very high capacity product without any dangerous reactions that occur like with the caustic in here. So this is an example of the catalytic carbons here. So generally hydrogen sulphide is going into the activated carbon. It's going through a catalytic reaction with the end product being sulfur, just elemental sulfur and water coming out basically. And so it's a very simple reaction. It has a very, very high capacity because it's catalytic. It generally has a very high capacity. We get a lot of questions from customers, well, if it's catalytic, why doesn't it work forever? We know that catalysts are not consumed during a reaction, so why isn't that catalyst adsorbents have a finite life to them, have a finite capacity? And the reason for that is those pores fill up with this hydrogen sulfide. And so eventually the hydrogen sulfide can't get into the activated carbon because the pores are so filled up with the sulfur, which is the end product of that. And so that's what diminishes the performance and the capacity of it. So once the activated carbon is full of sulfur, then it can be disposed of. The good thing about it is sulfur is non-hazardous. And so typically the sulfur that's captured in the activated carbon can be disposed of without any concern for hazards. I mentioned to you before, permanganate impregnated alumina, sometimes it's referred to as PIA. So the material composition is that activated alumina. It's impregnated with a permanganate, typically potassium permanganate. There's various concentrations that are offered in the market. How does it work? It's a chemisorption, like I mentioned. It uses oxidation. The nice thing about this product is completely non-combustible. This alumina that is the basis of it is basically a ceramic, as I mentioned, to it. So you could put a torch onto it and it might glow orange, but it's not going to catch on fire. So it's completely non-combustible, which is very nice for some applications. And there's a color change that occurs. So you can see a little bit of a color change here that's occurred in with some of the pellets, and that's just simply due to being exposed to contaminants that are in the air, sulfur dioxide or any exhaust or anything to that extent. So the product starts off with a nice purple color and eventually turns to a brownish color later on. So the color changes is a nice ability. There are products as well that are blends of adsorbent media. So in this case, here is a blend of an activated carbon product with that permanganate impregnated alumina, very broad acting. And so in this case, you're going after odor control with multiple technologies. So you're using adsorption here with activated carbon. You're using chemisorption with an oxidizer in there. So you're chasing lots of different odors with multiple technologies, we would say. The interesting part of this product is by adding the alumina product to it, it is fire resistant. And so it typically carries a UL fire rating, which is very important for a lot of cases. Certainly fire is something that needs to be avoided. There's also a low chance of off-gassing because you've got the chemisorbent involved, and you still get the color indicator. Even though the carbon doesn't have a color indicator, the permanganate media still has that color indicator. So one of the last adsorbents that we're going to speak about before we move into other technologies is regarding scavengers. So this is an example of a scavenger. It's a very specific color to it, and that color is probably familiar to you. It's kind of a rust color, and that's because it does have a strong iron base to it. So these scavengers are typically a clay with an iron oxide in the clay or in some other form. And that iron oxide has a high capacity for capturing specific gases, especially hydrogen sulphide. So this iron oxide will react with hydrogen sulphide. It's kind of a sacrificial product, we might say. So you could use this to reduce high levels of hydrogen sulphide to lower levels. So you'll very often see a product like this in an application where maybe you're starting off with 100 parts per million. So you'll use this product because it's low in cost to reduce that odor level or that hydrogen sulphide level from 100 down to 10, and then you could reduce the 10 to 0 using some other type of adsorbent, which is more efficient than a scavenger like this. So this is a very interesting product. The real attraction for this is that it's far lower in cost than, say, the catalytic activated carbons, while having a similar capacity to it. And so it's very attractive to those applications where you've got higher levels of hydrogen sulphide. So this would get changed out more often, but it's a lower cost product. And so from the overall cost standpoint, it works well for high H2S applications. This is typically what an adsorption system might look like. So you're going to have a mist filter to make sure that none of the mist and grease and such enter into the adsorbent, a fan, which is propelling the air through the adsorbent system. And then this is a vessel, kind of just a standard tank, which has an elevated bed inside of it, and the adsorbents are filled on top, and the air basically percolates up through the adsorbent media and comes out the exhaust here. So very, very simple inlet filter, blower, vessel, adsorbent, very low in maintenance. Adsorbent systems can be small systems. They can be horizontal flow. You saw a vertical flow before. Here, this is a horizontal flow systems. Here's the mist, what that mist and grease filter looks like that we were talking about. And the nice thing about adsorbent systems is you can use multiple adsorbents. We showed you that mixed adsorbent, which is one way of approaching it, but you can have separate beds of adsorbents. This is a horizontal flow system, so the air is flowing sideways horizontally here. So maybe you would have two types of adsorbent. This one might be for capturing hydrogen sulphide. This one might be for capturing your reduced sulfur compounds. And so you're able to have two different adsorbents in the system to capture all of your different odors in there. So also adsorbent systems have a ability to, the chemisorbents, modern chemisorbents have the ability to actually monitor the consumption of the adsorbent bed. This is kind of a dipstick type device, which allows you to monitor how much of the adsorbent has been consumed. There's also electronic versions of that adsorbent media monitoring as well too, where there's a probe that goes down through the adsorbent media. It measures the consumption of the adsorbent media, feeds that back to a computer system. So no longer do you have to worry about odor breaking through your activated carbon system and everybody panicking to get the adsorbent media consumed. There's a preventative way or a predictive way of knowing when the adsorbent media has to be changed out through electronic means there. So we spent a lot of time on adsorbents. That's certainly an area of primary focus for myself, but we also want to move into other technologies as well. So biological odor control is certainly very, very popular and a very well established odor control technology throughout the world at the moment. I'm going to break the technology up into two different terms where we use the term biofilter versus a bioscrubber or a biotrickling filter. So there's a lot of disagreement in the industry about exactly what these devices are called and the difference between biofilters and bioscrubbers and biotrickling filters. You'll find some people that basically say, you know, there's differences between these devices, but basically for our practical purposes, I'm gonna basically define that a biofilter is a system which is typically let's say less sophisticated, less engineered. It's typically some type of a box filled with a substrate. In this case, it happens to be bark or some type of wood, cellulose type basis, and air is percolated up through this. Bacteria will grow on this mass here, and this special bacteria will eat odors. It uses odor as food. It uses this wood bark or mulch as the basis to live on. It uses the nutrients in the wood as kind of a fertilizer and such, and uses the surface to live off of. So air, in this case, air is being pumped down to the bottom of an elevated bed, and it's coming back up through the top. And it's a very simple way of handling odors inside of the system. Typically, it takes a little while for the microbes to grow and to stabilize inside of the system. Of course, you have to worry about things like temperature and water. Very often, there'll be some type of humidification of the air to make sure that you've got a lot of wetness in there. These microbes need a lot of water, or there could be some type of a spray on top, which keeps this functioning. This substrate will last for a period of time. After a while, it does break down. The microbes do break down this substrate, and it has to be replaced. And so typically you'll empty it and refill it and just start the cycle all over again where you're having it work. So this can be very, very interesting. Typically the downside of the system is that it takes up a pretty good footprint. You can see here that there's some pretty big systems that maybe are just outside of this building. And typically the ratio of footprint to airflow is pretty high for these systems. But it doesn't require a whole lot of sophistication to it. So once you get the system up and going, they pretty much run well, as long as they're not getting heavily rained on or have dramatic temperature issues or anything to that degree. So that's a biological filter, a biofilter. Certainly an excellent and established technology, typically for lower levels of odors. And the bioscrubber and the biotrickling filter is what we would refer to as more of an engineered system. So it's typically manufactured from a fiberglass or poly tank, and it is a spray system where the microbes are growing on a engineered substrate of some sort. There's lots of different substrates. The key with this entire technology is the surface area. So the higher the surface area of the substrate that's inside of your biological tower, then the more microbes that you can grow and the more layer of microbes that you can have in order to react with the hydrogen sulfide. So gases enter into the system. There's a blower that would enter the hydrogen sulfide, typically hydrogen sulfide or other odor, into it. The odor travels up through the biological system. There's a spray system, which is typically spraying nutrients onto the engineered mass on the inside. Some systems are for recirculation of that liquid, and the liquid is recirculated and maintained of a specific pH, a pH that these microbes typically prefer to live at. Other systems will be a one pass system where whatever liquid is sprayed to the top drains out and goes to drain, and typically you're not maintaining a specific pH with that. So they work with some different type bacteria. These systems do require some nutrients. So you can see a tank here, which is basically a fertilizer that's being added into the system, which takes over from the wood bark that was here, which is providing some of the nutrient for the bacteria in this case. So the hydrogen sulfide in this case would be the food, or the gas which you're capturing is the food for the specific bacteria. The substrate here is the mulch or the wood bark. The substrate here is an engineered high surface area product, and the nutrient is being injected here, whereas the nutrient is just innate to the organic matter here with it. So that's biological, and here's a schematic kind of showing the two as well. So for a biofilter, you just have a blower. You're blowing that air through a humidifier, trying to get close to 100% humidity as much as possible. That blows into an elevated floor on your system. This can be kind of a system like we saw on the previous page, which looks like a dumpster basically, or it could be a poured concrete subgrade structure, just depending on what you've got to work with. And that air percolates up through this filtered media, and the odor is captured in here. There is going to be a draining of liquid from the bottom from this humidified air, and that drains typically back into the humidifier or drains to be treated. Here's the schematic of a bioscrubber. So again, we've got a fan that's blowing in the gas. The gas is actually blowing up through this packed column, and that's the big. In the industry, different people use different types of substrates, but the key here, of course, is surface area. As I mentioned, there is a spray system spraying in either recirculation water or sometimes once through water with that. As this bacteria grows, it eats the hydrogen sulfide. There is a waste product from the bacteria, which ends up getting captured and then goes to drain from there as well. So these systems It can take a while can take a couple of weeks to grow the biological mass that's in there, but once they're up and running, they're typically fairly reliable as long as the conditions are maintained stable. So these bacterial growths like to have very stable conditions with that. So taking a look at a biofilter, it's a very, very simple, low material cost, low maintenance and construction cost. Generally has some fairly broad odor removal, so certainly takes out hydrogen sulfide, but there are other bacteria that can grow in there to focus on other odors as well. It's typically good for low odor levels. Typically, we're not looking at a biofilter for high odor levels. Typically, residence time for a biofilter is about 30 seconds. Just a general rule of thumb for a biofilter is that you need to have the air inside of that mass for about 30 seconds. A bioscrubber, biotrickling filter, very often these are hydrogen sulfide focused. They're really excellent for applications where you've got high hydrogen sulfide applications. You can have recirculation or once through applications. Typically the recirculation are focused specifically on having really high performance at removing hydrogen sulfide, because the recirculation allows you to have the optimal condition for the type of bugs that like the hydrogen sulfide. A once through system will also take out hydrogen sulfide, typically at not the efficiency of a recirculation system, but it can also, that will grow additional bacteria, which might remove some of your other compounds too. Certainly more complex. There's pumps and pH indicator meters and things on there. So they're more complex than a biofilter for sure. Certainly not extremely complex. It does need freeze protection. I do see that Jeff Schwartz sent a note to us in the webinar chat asking about freeze protection. It's very important. This is basically a plumbing system, and the biological mass needs to have at certain temperatures in there. So it's very important to maintain a temperature inside the system. Fortunately, in most wastewater application, the air going through the system is maintained at an appropriate temperature, but freeze protection of any kind of pipes and pumps and such is very important for those applications. So typically in cold climates, you're going to need freeze protection of your piping and any of your other liquids as well. With that, typically you're going to be looking to be having some vessel for the reactor vessel for the biological scrubber to be also thermal resistant. Sometimes it can be insulated with that. So definitely important for it. These systems are especially well suited for high H2S levels. You know, it's not unusual at all to see these systems used at a 300 part per million level. We've certainly seen instances of these systems being used at 1,000 parts per million. So very, very high concentrations of hydrogen sulfide. Generally, a rule of thumb is that you're going to be looking for about 15 seconds of residence time. That can be reduced with some, the key is the surface area. If you have a higher surface area, then you can have less residence time because you're going to have more biological growth. Lower surface area means you're going to need to have more residence time because you're going to have less surface area, less biological growth with that. So let's talk about chemical scrubbing. Again, I mentioned in the beginning that I'm certainly not an expert in this area. I did consult with a friend or two in the industry to discuss chemical scrubbing and to get some information here. The key with chemical scrubbing is it can be fairly complex. So you see some examples of these chemical scrubbers. This actually looks a lot like a biological scrubber, and generally they're set up very similarly. It's just that there's a chemical reaction that's occurring instead of a biological process. In general, odors or gases are passed up through a column where there's a spray and a packing. A similar issue, you need surface area for the reaction to occur. The key here with the chemical scrubbing is the chemical use. So chemical scrubbing was, and it was much more popular in the past, but the chemicals which are used in the chemical scrubbing are typically very concerning from a safety standpoint. And in general, the liability of having those chemicals available and all the ancillary necessities of dealing with those hazardous chemicals make these less attractive. Certainly in many applications, it makes some sense. So you can see here is a wet scrubber, which is being used typically in an industrial process here, but you can see they can be very complex. So they're very good for constant flows, and in general, my contact in the wet scrubber industry says that generally, if you're looking at 20 to 100 parts per million for hydrogen sulfide, they are good, and also an airflow of typically 10,000 to 50,000 CFM. So wet scrubbers, chemical scrubbers, you're typically looking for higher airflows and where it makes sense for higher airflows, and typically for higher gas concentrations as well too. So taking a look at this, so chemical scrubbing is typically focused on one gas. You can have multiple gas systems, but it's basically multiple sections or multiple towers of different chemicals, because typically those, if you have multiple gases that you're focused on, you have to have multiple reacting chemicals, so and they typically can't be mixed. These systems have high concentrations of these reactive hazardous liquids. Maintenance is very significant in there. These hazardous chemicals are tough on pumps and sensors and such, so maintenance can be very significant for a chemical scrubber. They have to be designed also at the maximum gas level too, because you have to have the reaction set to be able to work at your maximum gas level. So if you have a fluctuating odor level or fluctuating gas level, that means the system has to be designed at whatever your peak is, where some other technologies are designed, like adsorbent technologies, are designed for your average gas level. Wet scrubbers or chemical scrubbers have to be designed for your max gas level. In general, though, they have the lowest overall footprint per unit of airflow. So you can get really high airflow through these systems in a low footprint with a chemical scrubber. So coming near our end, we've got just a few more slides. So there's a little comparison of technology. So we'll forward this to you to be able to take a look, but we've basically broken up into activated carbon. Advantages of our low maintenance and high efficiency, disadvantages, the periodic replacement which is required, and generally low capacity for hydrogen sulfide. Engineering and adsorbents, which kind of take a step beyond activated carbon. They're low maintenance as well, high efficiency, lots of different configurations. You can have multiple adsorbent medias and multiple flow directions and such. The disadvantage is it does require periodic replacement, typically less than activated carbon, but it does require periodic replacement of the adsorbent. A biofilter, generally there's no hazardous chemicals involved, so that's very nice. It's typically a low maintenance system. When it does require maintenance, it requires a lot of maintenance and getting in, changing out the biomass that's there, and that's not a great job, but typically that's only occurring every 3 to 7 years is kind of a number that I hear with that. So that works fairly well. Generally, they have a very large footprint though, so you're not going to see many biofilters in urban areas where land is a resource. These are going to be typically farther out away from urban areas. A bioscrubber doesn't have any hazardous chemicals. It's very often considered a green technology. It's especially considered effective in hydrogen sulfide. There's lots of other possibilities for it, but generally it focuses on hydrogen sulfide. Bioscrubber does have some significant maintenance, so you need to be aware of that. It needs to be watched. It needs to be, there's sensors and pumps and such that do need occasional maintenance. It does have significant water consumption, especially a once-through system is going to use a lot of water. A recirculation system will use less, but you got to have some water for it. the reality is bioscrubbers, a real world efficiency, manufacturers, including ourselves, are, we can get 99% efficiency out of a bioscrubber when we start up the bioscrubber and we're watching it carefully. The reality is, I think with typical maintenance practices of most customers, we're typically seeing a reliable average efficiency of about 95% with moderate maintenance with that. So certainly you can get the 99% out of it if you stay on top of it, but we generally focus on about 95% efficiency. Chemical scrubbers have a low footprint. Lots of vendors out there for them. They're very much available all over. It's typically fairly easy to design these. The companies that sell the packing towers offer lots of great support in with these chemical systems. The biggest concern is the significant maintenance and the hazardous chemicals involved with it. Taking a look at odor control technology, there's a comparison chart for each of these as well, as far as footprint, complexity, efficiency, multiple abilities to remove multiple odors, capital costs, and operating costs here. So we'll forward this to you to take a look at in regard to these. So I guess in conclusion, total odor control is possible. You've got to be careful about your selection of odor. Requires certainly some knowledge or assumption of the conditions that the system's going to see. I would say one of the most interesting solutions out there is the hybrid technologies that are offered, where, for instance, you use a bioscrubber to greatly reduce your hydrogen sulphide level, and then you use an engineered adsorbent system afterwards to capture any remaining odor with this. So these are very, very successful, and customers really like having this hybrid technology working together with it. Same with the hybrid technology of scavengers followed by an engineered adsorbent media. So I mentioned that you can have a system which focuses on high hydrogen sulfide level, uses a low-cost scavenger to reduce that hydrogen sulfide level. It won't completely eliminate the hydrogen sulfide or the other odors that might exist, and then you follow that by an engineered adsorbent, which is focused on really high efficiency and broad odor removal as well. So I wanted to thank you for your time today. Hopefully this webinar was helpful to you, to your understanding of the odor control market. You are certainly welcome to ask any questions. I'm going to switch over to taking a look at some of the questions that we've got come in our Q&A panel as well. So I guess I'll go to Q&A first. There is an attendee, an anonymous attendee, who asked the question, how often do you typically change media in a filter? So of course that depends, and we get that question a lot from customers. And if we tell them, if you can tell us exactly how much odor that comes in the system, we can tell you exactly how often you have to change out the adsorbent media. But generally, a good rule of thumb is for engineered adsorbent medias is typically 18 to 24 months. We typically work to size our systems so they last at least a year. We don't think any customer is going to want to change it out more than once a year, but we are typically seeing most of our customers changing out the adsorbent media 18 to 24 months. Now, if you're asking about changing out the biological media, the biofilter media, as I mentioned earlier, is changed out every 3 to 7 years. And the bioscrubber media typically lasts more than 10 years. It just depends on the manufacturer. So Zach Kaiser asked a question, is adsorption technology the only solution for portable equipment? That's a great question, Zach. I think the answer is yes. So I don't believe that I've ever seen a portable bioscrubber or a portable biofilter or a portable wet scrubber. So I think the answer is yes. That does seem to be the only portable odor control solution or transportable odor control solution. We do have, by the way, rental systems that we offer. So if somebody's looking for a temporary solution, we do have temporary mobile system for that. Appreciate the question, Zach. Zach's got another question. How do you size the amount of media for the application? So that's based on two factors: the airflow and residence time associated with that airflow calculates a volume, but also the gas level coming in. So we'll typically take a typically hydrogen sulfide level. If we know the level of the hydrogen sulfide coming into the system along with the airflow, then we can calculate the mass of the hydrogen sulfide that has to be captured on an annual basis typically, and then we will back in to make sure that the system has enough adsorbent media to last for the prescribed period of time. So typically at least a year with that. And so it's the sizing of the system and the adsorbent media is based on airflow and contaminant level. Appreciate the question, Zach. All right, so switching over to our chat. Let's see. Bob Glover. Hi, Bob. How are you? Bob asked, do we have a chart of typical gases and concentrations for various applications for greenfield projects? So we don't have a chart readily available, Bob, but there is some guidance in the WEF odor control manual. I can send you a link to that. That is just getting a new version published by WEF, some really great smart guys in the odor control industry, not me, put together an update to that. And so we can try to feed some information to you about that. Unfortunately, it's difficult to say typical because typical matters geographically, it matters certainly process-wise and such. So for instance, in Florida, where things are warm and the land is flat, typically you're going to get longer dwell times, and so you're going to very often see much higher levels of gases, hydrogen sulfide specifically, where in colder climates with a lot of elevation, you might not see that at all. So there's not a lot of great guidance on where to go from that. Very often our customers are looking for something nearby, a neighbor town or something that has a similar situation, and they're typically trying to get some data that way from it. Bob asked if the presentation is going to be available to share with clients. Absolutely, Bob. We're going to send, after this, we are going to send not only a link to a YouTube channel where this exact presentation can be watched and you get to hear me over and over again. And we're also going to be sending to you the PowerPoint presentation that can be distributed as well. So anyone that you know that needs to see it can watch and listen to this presentation as much as they like. Let's see, it looks like some of these questions have been answered ahead of time too. So let's see, is it, all right. For anyone who's looking for an attendance certificate to get professional development hours, please send us a note and we will be more than happy to send you a certificate there. So Jeff Schwartz had the question about these photos appear to be in warm climates. We mentioned this before. Yes, freeze protection is definitely an issue. Brad Calzone asked the question, can you use plant effluent water on a bioscrubber? Absolutely, Brad. In fact, that is the preferred way of doing it. If you can use some of your effluent water on the bioscrubber, the biological mass is going to be getting its nutrient from the effluent. So that is the preferred way of doing it. If you have to use potable water, then you have to add nutrient. And you have to be concerned about chlorine level in potable water as well. So very often we have to actually take the chlorine out of the water before it goes into the bioscrubber so that the chlorine doesn't kill the biomass as well. So very, very good question, Brad. And yes, effluent water is preferred actually in the bioscrubber. Let's see. Zach Kaiser said, you said the heat will cause the odors to desorb. Will bringing hot gas affect adsorption ability? Absolutely. For an adsorbent, a traditional adsorbent like activated carbon, really simply won't function at 200 or 300 degrees Fahrenheit like you've asked, Zach. You can work with some other chemisorbents in that temperature range. Typically tough to get above 200 degrees, but for instance, you can probably work with a scavenger to take out hydrogen sulfide above 200 degrees F. With that, some of the adsorbents actually require some moisture in them to work, like that permanganate impregnated alumina. So if you get above 200 degrees F, you drive off that water and it makes it hard for the adsorbents to work properly. So activated carbon certainly is not going to work at 200 or 300 degrees F, but there are some products that could work at these higher temperatures as well. Zach, another great question. Would bleeding in cool air increase efficiency? So that's actually kind of advanced odor control, Zach. So that's a really excellent question. And when we run into cases where customers do have a very high temperature, that is one thing that we can do is bleed in some outside air. Now, of course, that means you've got twice as much air that has to be treated, the same amount of mass of odor, but now, you know, the concentration is half as much, but the volume is twice as much. And so that does allow you to get into a case where you can bring the temperature down to an area that might work better. So if you do have a 200 or 300 degree temperature application and you can bring in some 80 degree air and get that temperature down well below 200, then suddenly you're in an area where a lot of chemisorbents can work a whole lot better. So really, really a good question, Zach. Have another attendee that has asked, you said that a bioscrubber has estimated efficiency of 95%. What's the efficiency of the other technologies? Hey, that's a really great question. Thank you very much. Let's see, I think I have that listed. I kind of skimmed over this one, didn't want to take up too much time, but the efficiencies are typically listed in this area. Activated carbon, you can typically get 99% efficiency. Engineered adsorbents are 99. We very often are seeing 99.9% efficiency with these engineered adsorbent systems. They're extremely efficient. A biofilter, you might see 90% efficient. It just depends on how everything's running and how it's stated, but 90% is considered a really nice reduction for a biofilter. Bioscrubber, as I mentioned, we typically say 95. I think there's a lot of people out there that promote a much higher number, and that's fine when it's under operation of the manufacturer, but when it's turned over to the client, we don't know if you reliably get a 99% efficiency. And a chemical scrubber, you can get really high efficiencies. You get 99% efficiency in a chemical scrubber there. So great question, anonymous attendee. All right. And Brad just commented back that he thought that we might have to dechlor potable water, and that's exactly right. With it, or at least it's preferred to dechlorinate it for sure. So, all right, well, if there aren't any other questions, I'll just tell everybody thank you very much for your attendance today. I hope it was useful for you. This was certainly not any advanced odor control. We will be offering webinars in the future, which might be exploring more advanced factors in regard to designing odor control systems as well. Today was hopefully a good introduction to you in the odor control industry. Hopefully you found it helpful. I certainly appreciate any feedback you can have, and certainly if you have any further detailed questions, we'll be more than happy to work with you. I typed in my email address and our general email address into our webinar chat, but you can always reach us through www.pureairfiltration.com or email us at info@pureairfiltration.com. All right, thank you very much for your time. Everybody have a great day and a great upcoming holiday weekend.